The complex numbers are in many ways better than the real numbers, and there's lots of things about the real numbers that are really annoying. So, for example, if you have a sphere and a plane, and you want to understand the intersection between the sphere and the plane, well, there's three cases. And it's either going to not intersect at all, or it's going to intersect it only like at one point and just be totally tangent to the sphere at that point. Otherwise, the intersection of a plane and a sphere is a circle. What we want is that no matter where the plane is and no matter where the sphere is, that the intersection is always a circle. And our problem is that we want to fix the real numbers, and just using the complex numbers instead of the real numbers, that's not good enough. We need to fix the complex numbers as well. The problem with the complex plane that needs fixing up is that given 2 points in the complex plane, they define a line. But given two lines in the complex plane, they don't necessarily intersect at a point, because if those two lines are parallel, they don't intersect. So you could sort of think about it that 2 points intersect in a line, and two lines intersect in a point, except when the lines are parallel, and this whole business about worrying constantly if they're parallel lines or not, we have to get rid of that. And what would be nice is if in the axioms of geometry, every time the word point appeared, you could erase point and replace it with line, as long as at the same time you also took every place where line already was there and you erased it and replaced it with point. And then in your theorems, what you could do is every time the word point appeared and line appeared, you could interchange them and just erase them and replace them. So then we don't want to worry about if we're dealing with points or lines. We just want to stay laser focused on where things are intersecting. To fix up the complex plane, we need to turn it from an open set to a closed set. So what we can do is take the left and right hand sides of the complex plane and glue them together like a mobius strip, which means that left hand and right hand get swapped. But then we're going to take the top and the bottom of the complex plane and we're going to also glue those parts together like a mobius strip. And then at infinity, we're going to twist this circle around and tie everything off so that when you go to infinity from a finite part of the complex plane into infinity, you're going to get twisted around twice in a Mobius strip so that left hand and right hand come back left hand and right hand, but you're going to come back from the other side. So if you went off all the way to the right, you're going to come from the left. And if you go off to the top right, you're going to come back from the bottom left, and then vice versa. Sort of what we did there was we took the circle at infinity, which is completely surrounding the complex plane, so that if you have any two parallel lines at a certain angle, then at the circle at infinity, those two lines are going to intersect on a point on that circle at infinity. But if it was a different angle, it would be a different point on the circle at infinity. So we took that circle and we twisted it up and glued everything together in this double Mobius strip way. You might wonder, why did we do this crazy double Mobius strip thing? Why didn't we just glue everything together like a normal way? That's a good question. And the answer is that each choice that you can make about how you glue together the different sides of the complex plane to make it a closed space is going to be a distinct topological space. And we really want to have our topological space be where we did a double Mobius strip gluing together. The other ways of gluing things together, that's a different subject. But right now, we're going to be gluing things together like this.